Okay, so I'm assuming that when I'm talking, everyone can see me on the screen then? Can someone confirm that we are live on YouTube and everything's looking good?
See you fine. Waiting for the YouTube stream to catch up right now.
Okay. I'm just waiting to see that we are on YouTube because we know there's going to be a few seconds delay, and then I will start.
Seems to be getting audio through. A-okay.
And they can see me?
Yep.
Wonderful. Okay then. Hello everybody and welcome to the first Reddit Robotics Showcase. My name is Ollie Smith, and with me you can see a few of the moderators who have helped put this showcase together, as well as a few of the participants for our first session. This event, when we started planning it back in January, about 6 months ago, we envisioned something that was going to be about 5 to 10 participants and one mildly interesting keynote speaker, a very small event. And this has exploded far beyond what we had originally envisioned. We have a 2-day event lined up with 4 categories: simulation, mobile robots on Saturday, and on Sunday, manipulation and legged robots. And we've got 4 fantastic keynote speakers. You can find full details on the website, and we're thrilled about it. We are absolutely thrilled that this has turned out to be such a success. Of course, there's been challenges for it being our first time, and we have a long list of things that we plan to do next year, at the top of which is that because we had our applications done anonymously, we only saw that when we were putting together our website towards the very end and running behind schedule, that we have a nearly all male speaking group over this weekend. So we've recognized that, and our primary goal for the next year is going to be doing better work for gender diversity. And we've been fortunate to have a great amount of support from people we've reached out to already. We've got a lot of resources and people we can talk to. So I will talk more about that at the end of the showcase, and you'll hear more about that in the coming weeks. Now I'll hand you over to Brian Gerkey, the CEO of Open Robotics, who made ROS and Gazebo and Ignition, the premier tools for advanced robotics software. If you're going to university and doing robotics, you're almost bound to be learning this at some point. He's going to be talking about the tools and how they fit in a bit within the simulation, but I want to stress that these categories were defined based on the participants, so they are somewhat of a loose fit. With that, I'll hand you over to Brian now. Thank you very much for participating, and I'll look forward to hearing what you have to say.
Thanks, Ollie. It's my pleasure to be here. Thanks for organizing. I'll go ahead and claim the mantle of a mildly interesting keynote speaker, and I'll see if I can live up to that. Let me share my presentation here with you.
Just want to clarify, that was our original aim. We far exceeded that.
I'll trust you. All right, does that look all right?
Yep, fantastic.
All right, thanks. Well, it's my pleasure to be here. As Ali said, my name is Brian Gerkey. I'm a co-founder and CEO at Open Robotics, and I'm going to talk to you today about simulation, and in particular, multi-robot simulation. This is something that we at Open Robotics do a lot of internally and with our collaborators and customers, and this is something that hopefully I will convince you is an important thing that you should be doing if you're serious about deploying robots. And I'll be happy to take questions. I think we've got time at the end. So first of all, who are we, Open Robotics? You may or may not know of us. We're coming up on, we'll be 10 years old next year, and we're a group of engineers and designers and artists who are building a lot of the open source infrastructure that people in the robotics industry have come to depend on. We've been working on this now, some of us for 20 plus years. For me, this work goes all the way back to when I was in graduate school and we first got robots in our lab, and we needed good infrastructure for using those robots as scientific instruments, which is what they were for us in that context. And what we got from the robot vendors just wasn't good enough. And so it's a classic story. We ended up just building our own infrastructure instead. We could get access to all the peripherals in the robot and then provide a developer-friendly API that you could use to write basically applications. In that context, again, it was experiments that would operate the robot. So Now, fast forward a long time, and we're at a point where we've got a really well-established ecosystem of developers and users, and a really extensive software stack that has become the de facto standard for developing and testing robot applications. We're best known in particular for two open source projects that we have the privilege of stewarding and contributing to extensively. One is ROS, the robot operating system. This is, if you could pick one thing we're known for, it's this. This is an SDK that you use to develop robot applications. So it has the developer tools, it has the libraries of algorithms, it has as well a connection to an entire ecosystem of people who are using and contributing and developing all of those tools and libraries and algorithms. And so if you see robots running around today, especially mobile robots in commercial settings, there's a very good chance they've got ROS inside. We are also the maintainers and stewards of the Ignition project. You may have formerly known this as Gazebo. It's the same project. We just gave it a new name a couple of years ago. This is an open source simulator. So this is the system that we use to reproduce what a robot is doing in its environment in a software simulation so that we can do development and testing. So we can think about ROS as being like an Android system for developing mobile robot applications, and we can think of Ignition as being a CAD kind of software for developing buildings, basically. Today, I'm just going to focus on Ignition. I could do a whole other talk on ROS. There's a lot of really exciting stuff that we're doing with ROS 2 these days, which is our main development focus. And maybe next go around, we'll talk about that. But I'm not going to talk about ROS today. I'll just talk about Ignition. Although many of the things I'll show you are using ROS inside because that's quite common. So I've argued that it's a de facto standard. How can we measure that? All of this code is open source. It's all permissively licensed as well. So that means that the things that we're building and releasing are either, if they're a bit older, that we license them under the BSD 3 clause. If they're a bit newer, then we use the Apache 2.0. Either way, very permissive licenses that let you, everyone, take the software, modify it, put it in your product, sell it, and you never so much as have to tell us that you downloaded it. Which is a fantastic thing. We did that on purpose because we wanted to encourage the widest adoption possible for these tools. On the other hand, that makes it difficult to know who our users are, because if they don't tell us, then we don't know. Of course, in the background, we can observe certain things. And so when we try to estimate our user community size, we can look at various metrics that relate to the online services that we host. I'll highlight two for you here. One is our documentation site at wiki.ros.org. This has been for a long time the kind of hub of the ROS community for hosting and creating user-facing documentation on ROS packages. And if we look there, according to Google Analytics, we're in the 150K users per month sort of range. We did about 1.8 million over the past year. I'll note in terms of global impact, when we look at the locations from which those readers are coming, a few years ago, historically, the US was at the top of that list. A few years ago, China overtook the US, and now we've got China at number 1, US at number 2, but together they only constitute 35% of our users, and the third place is below 10%, and it drops off pretty quickly, by which I mean to emphasize that we have a really widespread. This is not just something that's happening in North America or in Europe or in China. This is really a global community that covers just about every country in the world. As more evidence of that, there are partial translations of the ROS documentation into almost 15 languages, and we're really grateful to all the motivated users who are going through that effort. Another way that we can look at it is how many times are people downloading the software? So in addition to developing the code and hosting the documentation, we also have an extensive build and deployment infrastructure that puts the binary installation artifacts, primarily binary debs for installation on Ubuntu and Debian Linux, which are historically our top supported platforms. Those packages are hosted at the Oregon State University Open Source Lab, which we've been really happy to work with them over the years on this. So if we look at the stats from those downloads, we can take another kind of perspective on it. And we see that according to that service, we've got 750,000-ish per month unique visitors who are downloading software. And we're pushing a lot of packages. We did, I've got my month and year swap there. Sorry, it's 50 million packages a month over the past 12 months and a little over 600 million in the year. And again, I've got on the bottom line, same swap, 16 terabytes a month, 190 terabytes over the year. So we're pushing a lot of packages out. Those 750,000 unique visitors, they're probably not all humans. I think some of those are automated systems and robots. We know that some companies actually, their deployment process for pushing robots out into the world involves going upstream and taking from our package server and then pushing that onto their robots. So whichever way you look at it, we're in the hundreds of thousands to low millions of users, which I think would be a reasonable estimate, which if you think about the size of the global robotics developer community, that's got to be a pretty substantial fraction. Okay, with that as background, let's set the stage. So I said we're going to talk about multi-robot simulation. So what do I mean by that? So first of all, it's got to be multiple robots, right? It's right there in the title. So we're talking about a simulation that has teams of robots that are somehow coordinated in their behavior. And we're interested in finding out how it is that they interact and checking that we're going to get the right coordinated behavior out of this multi-robot system. It's also, for us, simulation is a full system. So while we don't generally simulate just isolated components like a single sensor or a single limb of a legged robot. These are the kinds of simulations that you might do more commonly in a system like, say, MATLAB, if you really want to do a very detailed numerical study of a particular component. There are other tools that might be better suited for that. Our focus is on building being able to replicate the entire 3D environment as well as all of the robots within it, and then being able to predict with reasonably high accuracy how they will behave in that system. We also focus on enabling the testing of the full software stack. So we tend not to build behaviors into simulation itself. We tend to build a simulation and then offer an API that ideally is the same as the API that you use when you program the robot. And for us, that tends to be ROS. And so what that means is that if you're simulating a robot in ignition, we would recommend that when you write a controller for it, you would write that using ROS, and then that will allow you, hopefully, if the simulation was done well, you'll be able to take that code and point it at the real robot. And that's always something that we want to support. And we also want to be efficient. We're always making pragmatic trade-offs in terms of what it is that we're simulating in order to keep things going pretty fast. Because we want to interact with autonomy software, because we want to interact with users, we try to keep things running at basically wall clock-like rates or better. And that means that, when we simulate underwater vehicles or flying vehicles, we're not doing very detailed computational fluid dynamics. We're taking shortcuts there and doing first order approximations. And that's an explicit trade-off that we make in order to enable an interactive developer experience. And putting this all together, our kind of mantra for simulation is we want the simulation to be the best possible substitute for the actual robot. If you don't have the robot right next to you, we want the simulation to be the next best thing that you can use to do all of your development and testing. A little sidebar, single robot simulations are also super important. We do a lot of that, and we do a lot of that with our collaborators. I thought I'd highlight, just because it's one of my favorite use cases, is space applications, just a few of the projects that are using ignition in what they're doing. So from left to right here, we've got the Valkyrie or R5 humanoid that NASA Johnson Space Center has built. And we did quite an extensive project together with them to simulate that robot in a planetary habitat preparation competition, which I'll get back to a little bit later in the presentation. In the middle is an ongoing project called Viper. This is with the NASA Ames Research Center. And this is a mission that, if all goes to plan, will launch in 2023, I think. They're going to put this rover on one of the poles of the moon, and it's going to dig in the ground with a drill and look for subsurface water ice and other interesting things that we think are just beneath the surface of the moon at its poles, but we don't know because we've never been there. And this is a system that's being extensively simulated using Ignition in order to answer a bunch of questions about how the system should be designed and what the remote operator interface will look like. On the right, we've got AstroBee, which is another project from NASA Ames Research Center. And it is a free-flying robot. It's a cube-shaped robot that is designed to go in zero-G or microgravity environments like inside the International Space Station. And a really nice thing about this project, and it really demonstrates the power of open source, is that we at Open Robotics didn't do anything on that project. This is something that the team at NASA did entirely by themselves. They picked up the software, they built an entire simulation with it. They also happened to control the robot internally using ROS, and they built all of that without our assistance, which is fantastic. That's how it's supposed to work. And this, I'll just show you one recent result from that effort, because there are actually 2 or 3 of those robots currently on the International Space Station.
This week, I was working with some free-floating satellites inside, actually. Whoa! We have one right here. And so we're using this technology to test out new things that'll help us on future exploration missions, namely to the moon and Mars. What we're hoping is to get these robots to be able to maintain our vehicles when we're not around.
So I love that application. I went to space camp in Huntsville, Alabama when I was in 8th grade, a very long time ago. I don't think I'll ever get to go to space, but some of the code that we worked on is in space right now, and that's really satisfying. Okay, back to the topic at hand. So what is Ignition? As I said at the beginning, it's a simulation. And I've argued what we mean by simulation, kind of what the scope is. So now from an engineering perspective, Ignition is, it's a modular, complete robot simulation package. We've got everything in there that you need to model the robot, from its kinematics to its sensors. We also simulate the entire environment around it. And this allows you to do a number of things. I'd say the primary use case for simulation, which I'll talk a lot about today, is really just supporting the entire development lifecycle from the beginning when you're designing a product or service or system, all the way through to deployment and beyond to support continuous integration testing. This is where we see Ignition being used extensively. And also, of course, these days, machine learning is a hot topic, and it's absolutely possible to use Ignition to train ML deep learning type systems. So why multi-robot simulation? I'm going to walk through 3 arguments for doing multi-robot simulation. The first is scaling up. If you want to deploy your system at scale, if you've got an idea for, I'm going to have a bunch of robots that are going to do sidewalk delivery, or I've got a bunch of robots that are going to do floor cleaning in an airport. At some point, ideally, you want to have a lot of robots out there. And before you put a lot of robots out there, you've got to convince yourself that you can have them all work together. Another is test coverage. And this is, I'd say, perhaps the most overlooked issue in robot development. The robots most robot systems are very difficult to get good test coverage on. And in our opinion, simulation is the only way to make that happen. And then finally, there's a what if aspect to simulation. There are lots of things that you either can't or won't or aren't willing to do in the real world, and simulation is where we can tackle those problems. So I'll go through these arguments in turn, starting with scaling up. So as I said, if you want to deploy, I would argue that we as a community, we as an industry, we're not working on these robots just because they're fun. They are fun, but that's not the only reason we're doing it. We're doing it because we want the robots to be deployed out in the world doing useful work. And we want them deployed in important places. And that's a really good thing. That's exactly what we should aim for. But that also makes scaled up testing hard. If you're going to deploy 100 or 1,000 robots into the world and you want to test that, you need physical access to 100 or 1,000 robots. You also need access to the place in which you're going to deploy it, which if that's a customer facility, it can be a difficult proposition. And also just the operational logistics of doing physical testing. It's absolutely necessary, as I'll argue when we get to the end. I'm not arguing against physical testing. You can't do without that. But the costs and the logistics of deploying robots physically and doing physical experiments with them can be tremendous. So to give you one example of the kinds of difficulties that you face when trying to scale up multi-robot physical experiments, I'll talk a little bit about an ongoing project that we're doing together with DARPA here in the US, which is called the Subterranean Challenge, or SubT. The goal here is to map and navigate and do search tasks in challenging underground environments. I show a couple of examples here. The way that this challenge is constructed, there's a need to cover tunnels, caves, and also human constructed or urban underground environments. The motivation here is, it should be pretty clear. There are often situations in which something happens in an underground environment like this, and there could be people lost or in danger in some fashion. And what we want to do is get in there as quickly as possible in the safest way possible and find and provide help to them. So the way that this challenge has been structured is there are these underground environments. They're completely unknown in advance to the teams that are competing in this challenge. They have a team of robots. Each of the development teams has a group of robots, and they're sending those robots in, and they have to go in autonomously and find certain artifacts that are in the world. And some of them they might be like a human dummy. It might be a backpack, might be a flashlight, something like that. They're going in looking for these artifacts and then reporting back their locations. So that's the search and mapping aspect of the challenge. So what makes physical testing hard in this case? If we look on the left-hand side, this is the setup for going into the physical tunnel test that was done. This is one of the groups of robots here. And you look at these robots and they're heterogeneous for one thing. They're heavily customized in this case. So the robots themselves are pretty complex. And it's the group that's going to do this probably doesn't have 5 or 10 spare robots that they can use for testing. They don't even, and there's often a large team, a development team behind this kind of effort, and there's generally just not enough robot hardware for everybody to have their hands on all the time. Another thing is, if you look at where they're going into, that's a particular, it's a research mine that was used for this experiment. Those kinds of environments might be hard to get into. On the right-hand side, you can see someone is there kind of setting up all the robots, and just the logistical overhead here, managing batteries and dealing with repairs and things like that. It's a real challenge. So let me show you what we've done in simulation. This is a highlight reel from a recent competition that we hosted. So this is all simulated in ignition. These are underground environments with teams of robots, anywhere from smaller teams up to, I think a team can be on the order of 12 robots, and they're going in all together. These are wheeled, tracked, legged, flying. They're going in and going through the environment and looking for these artifacts, as I mentioned, and reporting back their the findings that they have. So what's the impact of simulation-based testing in this particular environment? On the left, you can see the most recent physical experiment that was done in SubT was the urban circuit. That was February of last year. There were 10 teams. They built up 2 courses, and this is an extraordinary effort. I had the privilege to attend this event, and it was amazing to see the infrastructure that was built up, the sophistication of the courses, the way that they were instrumented to be able to collect all the data. And the teams were there for a couple of weeks, and the competition ran for about a week. And each team got 2 runs in each course. So overall, there were 40 official test runs. And that was a Herculean effort with fantastic results. And you can see, the aerial shot there of the teams and their robots. Now, what do we do in simulation? Our most recent simulation competition was the clip I just showed you was from November of last year. This was the cave circuit. And there we had 16 teams. we were able to build 8 courses, and then we ran everybody through all those courses multiple times. So we had almost 400 official test runs. So we're talking about an order of magnitude difference in the number of official test runs. And then in addition, in the time leading up to that competition, because we host this whole system in a cloud-based environment where the teams are able to practice, we develop practice worlds and official worlds. So there's a whole set of practice worlds that the teams can work in. And there were over 2,500 practice runs that we logged that the teams performed. So we can see a real scale difference between what is feasible in the physical world, even with very significant resource investments, and what is feasible in the simulation world. And so I think you have to do both, but the simulation world is the only way that you're really going to scale up your testing. So over to test coverage. If we're going to deploy these robots in the world, we need to be confident that they work. This is true of basically any system you're going to build and put out in the world. If it's not tested, it's broken. And confidence really requires extensive testing to be able to convince yourself and to be able to convince your customers, to be able to convince the general public if these robots are going to be out in the world interacting in a public place, to be able to convince perhaps regulators if you're developing something, say an autonomous vehicle. The core of building that case for convincing them that it works and that it's safe is testing. What's hard about testing these systems physically? For one thing, the test scenario setup can be quite hard. If you are testing if you're testing a particular situation where there's a particular physical configuration of the environment and the robots and the people, you can think of it as like trying to do, it's like you're trying to shoot a scene in a movie or TV show. You've got to get everybody just right and then call action and then have everything unfold just how you want it. And then you see what happens. And then, okay, that still didn't work. All right, everybody roll back and let's do that again. That is a difficult and expensive process to do physically. There's also a question of reproducibility. When you do it like I just described it live, there are probably little variations that are creeping in each time that you do it. It's difficult to do the same thing physically again and again once you get to the point where you've got multiple robots in a complex environment interacting with each other and other dynamic aspects of that environment. And additionally, you just don't know upfront what all the corner cases are. You don't know everything that you need to test. And the more testing that you do, the more you'll uncover those cases. So an example application to illustrate the importance of test coverage is a project that we've been working on now for a few years, primarily out of our office in Singapore, together with the Ministry of Health in Singapore. The goal here is to coordinate heterogeneous fleets of robots. And what do I mean by that? So if you walk into large facilities today in certain parts of the world, such as hospitals, which is the first use case that I'll talk about here, you will often see, especially if you go in the back of house, you will see mobile robots like the ones I'm showing you here. These robots exist, they're deployed out in the world, they are doing work basically 24/7, often like I said, in the back of the building, whereas a patient to a hospital, you probably won't see them. They're moving linen, they're moving foods, they're delivering drugs, they're doing a number of tasks. And they are generally really good at that. This is now a very well-established area of robotics technology. The robots are good at navigating. They're good at not running into stuff. They're good at calling the elevator and riding the elevator. They do all this autonomously. They do get into trouble, and there are humans who are overseeing what they do. There's a whole burgeoning industry now of what's sometimes called robot ops. This is kind of like DevOps, but for robots. These are people who are wrangling these robots that are mostly, but not completely autonomous. But on the whole, that all works quite well. The challenge now is that any large facility needs many different kinds of robots. They need some robots that can carry some payloads, some that can carry others. They need some robots that are doing interaction with people and some that don't. They need some that are cleaning the floor. There are a number of different types of robots, and it is true now, and I think it will be true forever, frankly, that there's no single vendor that can cover all those use cases. What that means is today, if you operate one of these large facilities and you want robots from multiple vendors because that's the only option to get all the functionality you need, you get some from vendor A, some from vendor B, some from vendor C, and they just don't talk to each other and they don't get along. And at best, they most of the time avoid running into each other. And so what this means in practice is when you roll this out in a facility, you spend a lot of time up front allocating space and time very carefully so that the robots from the different vendors don't interact with each other, because those interactions can be really problematic. And I would argue that this multi-vendor setup is not a bug, it's a feature. This is really what we want the case to be, because that's the way that will support having choice in this industry over the long run. So we've got these robots. How can we get them to work together? And so that's what we're building, is taking a lot of the same concepts that we've developed over many years in ROS, and we're using those concepts to develop the infrastructure that allows us to connect and coordinate these different robots in ways that allow them to share the space, allow them to share elevator banks, for example. This is a surprisingly common refrain in large facilities, is that they run out of elevators. Because the robots from different vendors can't share the same elevator bank. And so each robot vendor has to have its own elevator bank. And then you want to add another type of robot because it would do something really useful for you and you're willing to pay for it, but you're not willing to pay to build another elevator tower in your hospital. So there's a whole other presentation I could give you on the details of how we're doing that, but I'll talk really here about what we're doing in simulation. So why is this hard to test physically? You can see in the upper right, this is kind of that scene that I described earlier where, you get everybody queued up and then say action, and then, the things happen that you want to test. And what we're doing there, that's actually it's an in-hospital testing environment. It's a robot testing and staff training facility in this particular hospital. And this is the gold standard. This is the best that we can, that's really available in these environments. But it's also pretty unusual because in any facility like this, the space is really precious, and so are the staff. And to have the ability to be able to test in the actual hospital itself and have the actual hospital staff come and participate is uncommon. And even though we do have access to this facility, we can't do it that often. And it's also, it's still a pretty small test environment. Additionally, with these fleets, we've got unpredictable interactions between them that are going to be very difficult to uncover if we're just doing the on-robot testing. So what are we doing in simulation here? This is a view of a simulation that we built of a different environment. So I talked about how we're doing this for hospitals. It turns out that the same problem exists in any reasonably large facility that wants to deploy robots at scale. So what we're showing here is some of the work that we're doing in an airport setting, where we're taking all these same concepts, heterogeneous fleet coordination, and deploying them in an airport setting where we've got robots that are doing things like, say, moving materials around and also doing automated floor cleaning, which is increasingly a very common application in larger international airports. So in the simulation here, we're showing in particular traffic control. This is one of the core capabilities that we're building into this fleet management system. Is we need to know where the robots are going, and the different fleets give us different levels of access. So some of them might be a little bit friendlier to us and give us kind of, we can tell the robot where to go. But some of them really only listen to their own software, and their own software tells them where to go, but we might be able to listen in and find out where they are going. So we can't tell them what to do, but we know what they're going to do. And so we can basically make a plan around that. So, and we might be able to tell them to stop along the way. Maybe we can't tell them where to go, but we could tell them to pause. And then that gives us a lever that we can use to deconflict access to the shared space. Also, given that kind of setup, we can incorporate human pushed or driven vehicles and carts. And that's actually shown some of the systems that are moving around here are in fact humans that are driving small vehicles, or they're pushing carts. And in fact, in that earlier example I showed where the human was pushing the bed, that bed has a location tracking device on it. And so obviously our system is not going to command the human where to go, but we can know where that bed is going, and we can incorporate that into our plan. On top of the traffic control, we've also built a task allocation system. So one of the difficulties of when you have these multiple fleets in your hospital or your airport or your hotel is each of them comes with their own interface. And so you end up, if you've got robots from N vendors, you end up with N interfaces, and they're all different, and each only talks to its own robots. This is still a bit of a work in progress because there are certain things that to date, at least, we can't do outside of the vendor's own software stack, but there's some things we can do. And we've been able to show, again, in this airport setting, that we can have a common interface that sits on top that then we can use to say, okay, and like this is in the airport setting where the task is primarily cleaning. We can say, I need that area of the airport cleaned right now. And we can automatically decide which robot from which fleet will go do it, and then allocate that task over to that fleet and have it happen. We can also do interactions with automated doors and elevators. I mentioned elevators earlier. In these large facilities, the elevators are a main choke point. But the robots absolutely need to ride in the elevators. These are towers that the robots need to use the elevators to navigate through. And so testing the interactions as the robots get access to the elevators and demonstrating that we can actually solve that problem that I mentioned at the beginning, which is, can the robots take turns accessing the same elevator bank? That's the kind of thing that we've been able to demonstrate in simulation and show that it works well enough that we can show that to the facility operator and say, look, we've got this result in simulation. We're confident enough in it that we're ready to come test it, and use your precious space, use your elevators, use your staff for the day, and show that we can do it for real. I'll also note that another aspect of testing in simulation is finding problems in physical testing and then reproducing them in simulation. This is quite common. I remember an anecdote from one particular company that develops floor cleaning robots that came to visit us some years ago, and they're using Ignition. They're using ROS on the robot. They're using Ignition to simulate it. And they said it was an absolute lifesaver for them because they had a particular issue with the robot where it would encounter a negative obstacle, a small gap in the ground, and basically the wrong thing happened. They had a really hard time reproducing it physically in order to be able to debug it, but they were able to reproduce it in simulation, fix it in simulation, and then come back to the physical environment to confirm that the test worked. And then what happens after that, if you're doing it well from an engineering perspective, is you take that simulation setup and that becomes an automated test. So now you've got part of your CI system is running these automated tests, and you're therefore preventing regressions of these problems that you encountered first physically and then reproduced in simulation. So let's talk about hypothetical experiments. So we often, when we're getting into a new project, a new product design, we don't know exactly what we want to build. We might have a general idea of what we're trying to do, but it's not fully defined yet. And often those design questions go beyond just the physical robot. We might be talking about we're not just designing a robot to work in a given environment. We might be talking about designing a robot that, for it to be deployed and to be useful and to work well, requires modifications to the environment. And so there's this really large configuration space, this design space that we're trying to work through. And you just can't build every option as you're going through that design space. You're not going to physically build every configuration of a robot. You're not going to build every configuration of a building in which it's going to operate. You really can't run your full scale experiments in real facilities because the facilities are in use. A lot of the places where we want to have robots be introduced, it's not greenfield. It's not a brand new building where you can go in before the people come in and do your robot testing. It's a live facility now that's used basically 24/7, and you've got to figure out, you've got to answer in advance, well, what if we do this with the robots? What if the robot behaves like this? What if we lay out the space like this? What will actually unfold in the physical world? And then, of course, the solution that you're trying to build, the tech might not even exist. And so you might be asking yourselves, well, what if I had a sensor like this? Or what if I had a robot that had these terrain traversability characteristics that doesn't exist yet? But if I did have that, then the following would happen. And so, okay, now I know I might want to go invest in that. So to take a couple of examples here, one project that we did together with a customer, and this is a real customer. This is a live facility, a very large facility, and they were considering a major renovation. There were some aspects in the environment that were not movable; they were given, but there were some aspects that were going to physically reconfigure the space. They had two primary options for the layouts, and they would result in different traffic flow patterns. And this is traffic for both the people and the robots. This is a facility that's largely occupied by people, but also has a lot of robots that are doing various tasks. So they came to us and asked us for help. And what we did is we simulated the environment. We simulated both of the physical layout options, and then we simulated the daily operations because there are, changes that happen during time of day, different patterns that can be observed. So we simulated the flow of the robots and the people moving things through the environment, generated basically heat maps showing where the vehicles were over time, and then that kind of tells you like where do the robots and the people all tend to spend their time. And in some cases that time is spent waiting. In a lot of cases it is, like if you're waiting for an elevator, waiting to cross an intersection, things like that. And so that was a really nice result that we could take back to the facility operator and say, okay, here's basically what we believe it will look like if you take option A versus option B. And that was a key factor in their decision, which then influenced, a significant large facility construction project. And this was an outcome that it was a request that I was a little bit surprised by, but it is in a way a kind of natural evolution of the work that we've been doing in simulation to be able to apply it to this kind of problem. I'll give you one other example on the hypothetical side. This is so much older work. This is about half a dozen years ago. The project that we did together with DARPA, and they were interested in what are the limits of the capabilities of teams of robots that are going to do search and rescue tasks. This project was in some ways a precursor to that sub-T program that I described earlier. So the question here is, well, what matters? If I want to have a large team of robots that are going to go out and do a search and rescue type task, does the sensor range matter? Does the communication range between the robots as they're out in the field without any infrastructure and having to build ad hoc networks, does that matter? How about the robots' relative speeds? How about their fuel or duration kind of capability? And obviously those all matter, but the question is, where are the inflection points along each of those kind of design axes? So we varied all those characteristics and then tested with a bunch of different search strategies. And I'm showing you just one example here of robots doing, I think these are all ground-based robots doing search activity. And then we tested all those, and then measured a variety of things. Basically, how long are they out? How far did they travel? How long did it take to find the person of interest? And how accurate were they in reporting back the result? So this is the kind of this is that kind of investment direction kind of experiment that can be done in simulation. Because if the answer comes back that, well, the absolutely dominant factor here is communication range. If the robots each can carry a radio that can communicate over 2 kilometers instead of 1 kilometer, then that tells you should go either buy those radios if they exist, or if not, invest in developing them. That's where you're going to get the most payoff. And those are or if it's in sensors, then work on sensors. So those are the kinds of results that you can get from these hypothetical experiments. Now, I've talked a lot about simulation. It's not the only place to be. In the end, we want all of this to work in the physical world. As I argued earlier, our approach to building these simulation systems is to offer an API that can be used in the same way in simulation as it can on the real robot. So we're always structuring things and trying to guide users to develop their systems in a way that can transfer to the hardware. I would argue that simulation it's absolutely necessary, but not sufficient. That's not going to be good enough to do everything that you want. And so you have to regularly check your assumptions. And these are assumptions about the robot. There are assumptions about the environment. There are assumptions about the other components of, the other agents that exist in that world. If you're simulating humans, then is the human crowd modeling or behavior modeling, is that correct? You've got to check all this stuff regularly in the real world. So I'll give you one example of a nice result of that happening. This is going back to that NASA Valkyrie robot that I showed earlier. So this is 2015, 2016. We did, it was called the Space Robotics Challenge together with Johnson Space Center. And so we worked with them to simulate this robot in this Mars-like surface environment. And the setup here is that the robot is going to go in advance of humans, and it's going to do planetary habitat setup tasks. So it's basically getting everything set up before Matt Damon shows up so that it's all ready to go. This was what's called an eyes-off teleoperation task. And so there is a human in the loop. It's not completely autonomous, but the human is not physically there with the robot. The human is somewhere else with a time-delayed connection and only has access to the data that the robot can sense. So the robot has cameras and other sensors, and it can relay that data at low data rates with high time delay back to a human operator who can take that and then decide what commands to send back. So the challenge here was, how do you design that data flow and that human interface so that you can get effective control of this robot? So this was a whole challenge. It ran, there was a winner, and that winner then had the privilege of trying that work on the real robot, because this robot does physically exist. So this is a shot from the very first day that the winner of the simulation-based challenge had the chance to access the physical robot. And the quote I got from him, and you can just see him appearing sometimes from behind the northeastern banner in the upper left corner. What he reported back to us was, the good news is that the process of getting the software running on the real hardware for the first time and completing the task with perception was done in one day. So this is an incredibly complex robot. There are only a couple of these in the world, and this person had never had physical access to this thing, had never seen it, had only worked in the simulation environments, built this entire complex application, and was able to take that and translate it to the robot and get approximately the same behavior in one day. So that's exactly what we shoot for. I don't want to give the impression that it happens like that all the time, but this was a particularly nice result, and this is what we hope to get out of simulation as much as we possibly can. So I'll just close by saying, in my opinion, to be serious about robots, you need to be simulating. I remember when I was in graduate school, the mantra in our lab was, simulation's cool, but doesn't matter until it gets on the robot. And I think that is still true. If you're trying to have impact in the world, you need to be running physical robots. But I would also argue that if you're just on the physical robots, that's not nearly enough. There's no way in which you're going to do enough testing. There's no way in which you're going to do enough exploration of design spaces. And there's just no way you're going to convince yourself that any large deployment of robots is going to work if you're not doing a lot of simulation. So with that, I will give you one pointer, which is a few pointers here. You can check out our open source projects, what our company does. And I will also invite you all to come to ROSCON. This is our annual developers conference. It went all virtual last year. We're going all in person this year, and it's going to be in New Orleans in October. And if you're able to come, it would be great to see you there. If you can't come, we also do a live stream for folks who are not able to come, and we record all the videos afterwards. So with that, thank you very much.
Okay, thank you very much, Brian. Really appreciate the presentation. Would you mind muting the mic just because there's a bit of backup and a delay? Wonderful, thank you very much. Yeah, fantastic presentation. And again, thank you so much for participating. We've got about 15 minutes to ask a few questions, and I've got one that I'd like to ask at the start, if that's okay. So amongst my friends, alumni, colleagues, the number one issue that people have with ROS, and then by extension Gazebo, now Ignition, is the learning curve. They see a somewhat steep learning curve and a challenge to get up to speed, and there's almost, at our university, there's almost kind of a make and break point of those that do and don't manage to get over that initial hurdle. So for going to the effort of something like setting up a multi-robot simulation, I'd love to be able to do something like that. But what kind of resources are there, and how feasible, and what is the learning curve to get to that kind of a point?
That's a completely fair question, and that lines up with the feedback that we've gotten consistently over the years, which is we need better documentation. And in the long run, I think that is the answer. That is something that we've invested heavily in, during the whole lifetime of the project, but in the last couple of years as well. We put a lot more effort, in particular, into the tutorials around Ignition. So I hope that they're going in the right direction. There are also a number, because this is a big open source community, there are a number of other people outside of our group who are actually developing their own documentation. So I'd say that, we make the best documentation that we can, but we're not the only source for it. So there are a lot of groups outside of our company who are developing their own video tutorials. They're developing how-tos. They're writing entire books on these software ecosystems. So I think at this point there's quite a lot of documentation out there. I think that it is largely enough to get somebody going, but perhaps it's not as well organized as it could be. And so I think that, I know that there's more work for us to do to make that documentation more accessible and more intelligible. So that's something that we're working on. Documentation is it's kind of like testing in a big software system. You're never going to have as much as you want.
Okay, thank you very much. I'd love it if at some point you could send me an email with links to the videos that you've used in the presentation, so that we can share them with our community, just that people could want to see those videos can. And if you happen to have any recommended resources, like you said, outside of the community, if there's a couple that you can say, these are the books that I would recommend, I'm sure people would love to hear about them. Is there anybody else who has a question?
It looks like we have some questions on YouTube, if you want to share those. All right. John Till asks, how does Ignition simulate human traffic in the hospital scenarios? It seems like a hard problem. How difficult is it to include this effect, and do you know how accurate it is?
So there are two different approaches that we use there. One is it's a system we call actors, and so you can have an individual human can be designated as an actor and have basically a scripted behavior associated with that actor. So what you can say is, well, this is a person who follows this kind of pattern, and it can have waypoints and be repeated. So we can have individuals who are basically just walking scripted routes. That's one thing. There are also the human pushed carts that I pointed out, and so that's done differently. We basically control that more in simulation. We control that more like we do the physical robots. That's more like an agent that has its own autonomy stack that doesn't run in the real world because the human does that job. But in simulation, we run that like a little autonomy stack that drives the person and the cart around. Is it realistic? I think at a small scale it is. I think that what we are missing right now is the larger scale crowded environments. Consistently, when we show our simulation results to the operators of these large facilities, the very first thing they say is, where are all the people? And we feel like we put a lot of people in, and we're happy that, we're getting the kind of performance that we are with the number of people that we put in, but they're like, no, that's not nearly enough people. You have no idea how crowded this place is on a regular day. And so I think that is still a challenge, is how to get the realistic traffic flow of the people in indoor, very crowded environments. That's something we're working on.
Okay, Chris, are there any more from YouTube?
Yeah, we have, looks like one more question. Michael Greer asks, do you know of any companies that are running automated tests using Ignition? Something like running comprehensive test environments for every merge into the master branch of a Git repo.
So every comprehensive test on every merge, I don't know that for sure. And if you think about it, that is, especially if the implication there is that you're doing pre-merge testing like that may be quite hard, because you could have a large battery of tests, even if you've only got a handful. Spinning up a simulation, as efficient as we can make it, still spinning up a simulation and running some autonomy stack and testing some condition at the end is going to take more than a little bit of time. And it's, in my experience, it's uncommon to put a test that has that potential delay as a blocker to do a merge. I think it's much more likely that these tests are being batched and run on a periodic basis, like say overnight. That tends to be how we do it when we're building these systems. So I think that's more common. And I absolutely know of companies that are doing that on a regular basis. This is happening both in the AMR, autonomous mobile robot space, where you've got these mobile robots that are moving things around in the world. It's also quite common in the UAV space. If you look at what's happening with the PX4 autopilot, there's an entire software in the loop testing setup that can be done in simulation, and they have quite a good integration with Ignition or Gazebo. So you're able to do automated testing in a CI context of the autopilot and its autonomy stack on top, all in a 3D environment.
Okay, wonderful. Thank you very much. Oh, we have one more question that's just come in now. And then I think after that, we'll take a quick pause before the next participant for the next presentation. The question comes from Ian, who is up next, actually. Is there a way to run a scenario sim in Ignition faster than real time? We wanted to run hundreds of tests in several minutes. Can that be done?
It depends on the complexity of your test and the computational power of your computer. So there's nothing in Ignition that makes it only run at real time. Basically, you can set how fast you want it to run. You can lock it back so it's going to run, a fixed frequency less than real time. You can give it a target to run hundreds of times faster than real time. Whether that's doable depends on the complexity and how much compute power you've got. I will mention that one of the key abstractions that exists in Ignition is being able to choose different physics engines for different tests. And so we currently support multiple physics engines that have different approaches built into them for simulating the physical world, including all the way from high-end, full either rigid body dynamics, basically rigid body dynamics, down to what we call a trivial physics engine, which is a basically 2.5D kinematics only approach. And that's a much lower computational load. So when we scale up our experiments, like in that kind of hospital setting, that's where we go. We go to the lower fidelity, but lower computational requirement physics engine, and then that gives us higher response times, or higher response speeds.
Okay, wonderful. Right, thank you very much, Brian. Thank you for your time and your participation in this event.
Happy to do it. Thanks a lot for hosting.
Wonderful, and I look forward to staying in touch if there's anything that Open Robotics want to share in the future more directly, and likewise we'll let you know about future events that you may be interested in. Wonderful. Okay, thank you. Everybody, we're going to take a couple of minutes break and we'll mute our cameras and audio, and then we'll be back for Ian of SBX Robotics. Thank you, Zoom, for telling me that I had my mic muted. Thank you, Nathan, as well. So I've just checked the YouTube comments and seen that a few more people had asked questions just after Brian had left. We will copy those and see if we can get an answer at a later point, which we can share back on the Reddit post. But I recommend that people who have questions for future participants, that you start typing that out as they finish their presentations, that they get time to send it, because there is, of course, a delay with the live stream. Right, now I'm going to hand you over to Ian of SBX Robotics, who's going to tell you about a very exciting simulation set of tools that they developed. Ian, thank you very much, and take it away.
Thanks so much, Oliver, for having us, and of course organizing this this great showcase. Yeah, so I'll just share my screen here. All right. Yeah, so as Oliver mentioned, I'm Ian Dewancker, co-founder and CEO of SBX Robotics. And we focus on building synthetic data to achieve vision capabilities in robots. So the first thing is, why are we excited about robot vision in general? And I think we view that as sort of a critical capability for robots, kind of in the 21st century. And the truth is, there's just a lot of very dynamic and very complicated tasks that are showing up in industry. And it's the case that pre-programmed robots can't really properly adapt and achieve success in those tasks. And so some examples of these types of robots, you have arms maybe sorting through e-commerce items, or inspection robots in warehouse storage facilities, reasoning about inventory and kind of the complex packaging that shows up in these settings. And so it's important for these robots to be able to, have perception capabilities and adapt to those environments as they're running. So what sort of vision capabilities are these systems seeking, or what is capable today? And one of the important tasks that shows up in a lot of robotic vision applications is instance segmentation. So reasoning about objects in an image and understanding the visible sections of those objects. And the reason that's important is robots need to use this info to, maybe inspect an item, count how many there are in a scene, generally reason about the wear and frequency of particular objects in a scene. And it's very exciting right now because, in the last 5 years or so, we have some very powerful techniques from deep learning and computer vision research that work quite well on these tasks. One model in particular that is pretty commonly adopted in many of these scenarios is this mask RCNN model that is a deep learning model, but has really strong performance on a lot of object segmentation tasks and scenarios. Another task that shows up with some frequency in robotics is reasoning more specifically about the relative position and orientation of particular objects. And so this is important because for a robot to manipulate those items, they have to be able to reason about where that item is relative to its own sensors, its own frame of reference, to maybe be able to pick it up or move it. And so here again, some deep learning approaches are starting to show a lot of promise and work quite well. In particular, one approach that has been adopted in some applications has been reasoning about object key points using a deep learning model, and then solving kind of a known correspondence between key points on known objects and where those key points are on the 3D model of that object. And so the great news is these deep learning approaches work quite well. But the issue is there's a lot of data requirements, heavy data requirements, to get these models to really perform well in practice and in the applications we need them to work well in. And some of the pain points with collecting that data is it does take some time. So you have to actually have the hardware resources, paying people to run SKUs and items through a system. It may just take a long time to collect, the tens, the hundreds of thousands of example cases that you need to build one of these deep learning models successfully. The other point that's quite a painful thing with this technique is it costs a lot of money to annotate the data. So typically, it's not just collecting the images, but you also have to pay someone to very carefully and with a lot of detail tell you the boundaries or whatever information you're trying to extract from the images, and it's quite costly and slow as well. And the other issue is that when you ask people to do these sorts of annotations, they can make mistakes. So that example image on the right there, you can see kind of the heavily detailed scenes that these industrial robots are trying to reason about, and asking people to sort of very, very carefully define the boundaries of these things, becomes difficult at scale. So, part of what SBX is very excited about is the promise of training with synthetic data, because we believe it's faster, cheaper, and more robust to build these deep learning models and ultimately solve the vision tasks that you need for your robot application. So how does the SPX system work? We really see kind of our core, offering as kind of a data multiplier. So we think, it's a pretty simple flow to ask a robot developer to collect a few images of their task at hand, just a few dozen. And then SPX basically creates a synthetic environment that can render tens of thousands, hundreds of thousands of image variations with annotations already that can be used to build a successful deep learning model. And we don't just create any data, we also measure the quality of that synthetic data by training our own models internally and reasoning about how well they transfer on real images. So a little more detail around kind of that first step. Again, we ask robot developers to share a few images that describe their scene. So in this case, we have a robot reasoning about some blue bins on a shelf. Ask them to share a bit of information about the sensors they're using and perhaps the physical specs of the items of interest that they care about. And then SPX task is to essentially source assets, 3D assets that represent that problem, and also create generators on demand that reflect kind of the spatial positioning and the relative positioning of those items in the scene. So you've got on the right-hand side a synthetic image that was produced by the SPX generator software with similar looking bins and orientations. And then the second part of the step, which is really critical to kind of ensuring high quality synthetic data, is benchmarking it. So as part of the SPX delivery process, we run lots of variations of synthetic data, varying things like lighting, textures of the items, backgrounds, orientations, all of this important aspects of how ultimately the images and the computer vision data looks. We sort of aggressively explore that space. And so on the left there, you have an image of one such study that we do on every project, where those lines all represent the performance of a model trained on synthetic data and evaluated on real images. And the higher the better there. And so that actually ends up being a decent amount of compute and GPU resources to sort of complete that entire cycle. But at the end of the day, you end up with a synthetic data set that you have high confidence generalizes to the task at hand. And so on the right there, we have a inference shot from one of our benchmarked internal models, which is actually just an open source software object detection model running on a real image and doing quite well detecting those bins after only being trained on synthetic examples. So what does the data set format look like for SPX? We use a lightly modified version of a standard format called COCO, which stands for Common Objects in Context. That's a format that's been used in several image computer vision contests and research. It's very easy to use and reason about data format. And these images give you examples of the sort of data that SPX generators produce. So this is a forklift detection generator, and you have a color frame on the left, which kind of is meant to reflect the image sensor that the robot's using. The middle frame represents all the rich annotations that we provide, so masks, bounding boxes, orientations of the item, so forth. And on the right, we also offer depth information about every pixel in the scene, which is important to reason about in some applications as well. So the benefit here is that, of course, the generator that we develop can create millions of these image variations quite quickly. And the benefit then of having a data set that's highly diverse is you're more likely going to be able to build a computer vision model that is robust to kind of the visual variations that show up in the production system and the robot's task at hand. So yeah, that's at a high level, what we've done, what we offer kind of as a service, as a company. The high level takeaway from the benefits of synthetic data is that it really is a faster, cheaper way to bootstrap or improve a deep learning vision model. One of the truths of building a computer vision model in any application is, you've got sort of a continually evolving understanding of what items are present in some of these complex tasks. Maybe you're deploying a robot to new scenes over time. And the benefit of using synthetic data here is that, instead of having then to re-wait before you collect all this data and have it annotated, you can sort of get a few examples and quickly update your data to those new applications. And in general, yeah, the real complexity in getting synthetic data that works well is having really great technical art and then having enough compute to sort of run those experiments through and reason about that generalization. And that's sort of what we do at SPX. So yeah, if obviously if anyone is building computer vision projects, very happy to chat about it. Even at a hobbyist level, we do have a free tutorial that we released last month that gives you sort of an example of what synthetic data looks like, how to train on it using a mask RCN model that, again, as I mentioned, is an open source model from PyTorch and Torch Vision. Yeah, we're really excited about the future of synthetic data. Ultimately, computer vision running on more robots for these interesting tasks.
Okay, Ian, thank you very much. We have a couple of minutes, and I just want to say, so the next participant only just turned up, so I was beginning to think that we were going to give you a bit of extra Q&A time there. So for future participants, please be aware that we will be sticking to the kind of the 10-minute time slot. With that said, Ian, thank you very much, and great to hear that you're offering support for anyone at any level. Hopefully you don't come to regret that, and you won't be flooded with people now. And thank you for putting together a tutorial as well, because this is very interesting work, and it's something that I know a lot of people want to deploy to their robots, but see as very challenging and daunting prospect. One question I've got asked from someone on YouTube, Nathan, is how important do you see lighting to these simulations?
Yeah, so that in many applications is one of the critical aspects to vary in a computer vision data set. And the high level reason for that typically is high contrast aspects of an image or an item in a scene are very often what these convolutional neural nets will pick up on very, very easily. And so if you don't get the lighting right, you don't have those high contrast regions sort of represented well, you're not going to kind of achieve optimal performance. So that is something that is quite important, yes. And I didn't mention the technical aspects, but we are using a game engine, Unreal Engine 4, to drive sort of our back-end simulation. And there's a lot of powerful lighting and rendering, abstractions there that we leverage as well.
Okay, thank you very much. I'm not seeing any more questions. We have just hit our time. So thank you very much, if you wouldn't mind killing your video stream.
Thank you very much, and thanks for having us.
Wonderful, thank you very much. And I will now pass us over to Mirza of BabaCAD, who is going to tell us about their simulation and control software. So, Mirza, are you ready?
Yes, I'm ready. Do you hear me?
We can hear you, we can see you just fine. Do you want to be sharing your screen, a PowerPoint, or are you talking just to the camera?
Yeah, I will share my screen.
Okay. Wonderful. Take it away.
Thank you guys for organizing this great event. And my name is Mirza. I am the owner and author of BabaCAD and also BabaCAD Robotics software. And I will talk about BabaCAD and also globally about some challenges which are put before robotic simulation software. I will start with some facts about that. Now we have a very very small robotic number of robots available to small and medium enterprises, and also about statistics. Small and medium-sized enterprises represents the most of business in the world, especially here in Europe, where I am from, and also we can see that many robot manufacturers come now from Eastern world, especially China, and so on, and these companies already mastered the technology of robotics hardware, especially AC servo motors, harmonic drive reductions, and other stuff, and it's great to have that, but and also prices are going down in the last few years, especially, but one thing that's maybe missing, and it's weak in this configuration, is simulation control software. I'm in this branch about 20 years. I'm engineer of electronics and robotics, and I made my first simulation software about 20 years ago. I also have some IEEE presentation at that time, and it was very, how to say, it was good software, but later I found many things that's missing, and one of that thing is environment. I have a good simulator which also I connected to real robot. In that time it was Mitsubishi PA10, very good industrial 7 degrees freedom robotic arm. But later we found when we testing and when we connect a robot to software to the robot, we just can play and do some simple testing. But when you don't have an environment, it's very hard to test robots. It's not a matter of, it's just a single all multi-robots, and from that time I think about to start of making some better simulator, but I had to pass that long period of making CAD software, which is now a basic platform, and it makes simulation more powerful, and I can say some basic feature about BabaCAD robotics. It's based on BabaCAD, which is a professional CAD platform. You can import existing environment from any other commercial CAD software. Is programmed in C++ using OpenGL. It's very compact. It's not too heavy, and there are no some external buggy and big libraries. And also I made BabaCAD robotics open for customizing. There is Python API and also C++ and C#, and .NET programming interface, which allows users and developers and companies to make a better software to program their custom functionalities, and also to easy connect simulator to the real robot. And also BabaCAD has now a few already established, very established software robot configurations, like for example KUKA, Fennec, Motoman, and a few others. And also it's very easy to import any other industrial robotic arm. And also I plan to go further with the next version, where not only robotic arms but also other robotic configuration can be simulated. And here you can see also it's one part from one screenshot from Python API, where users can easily use BabaCAD Robotics API to connect robot and also add some custom functionalities. Also, I can say that this software has all functionalities that all others commercial robot simulation software has, as trajectory planning, curve tracking, pick and place, and other task programming, offline programming tasks. Also, there is a very special feature of real-time control, where you can move robot with just the mouse and picking and one control key from keyboard to switch between z-axis and xy plane. I will try maybe to see if I can share screen from application. Do you see? I hope you have.
Yes, I can see it. Yes, just so you know, you've only got about a minute or two left. So if you, I'm going to share this quickly, and then we'll move on to the questions, if that's okay.
Well, okay, I will just try to move, and I hope you will see that I'm controlling the.
I do want to see this.
Yeah, this is FANUC 6 degrees of freedom robotic arm. I can move any joint. Also, this is direct kinematics, but I also pick robot manipulator, and then inverse kinematics will be calculated in real time, so I can move robot around. Also, it's we have here a category menu in a top menu bar, where you can select any of robotics functions, for example, to insert some to save current robot position. Then later I already saved some positions, and you can click to simulate to see how robots will move. And also there are other functions of how you can copy this robot to other position, which all trajectory saved and copied to other robots. Also, you can insert another robot. It don't have to be the same model. You can, for example, I will now insert the one Motoman and so on.
Mirza, thank you very much. I really appreciate your presentation. I just want to make sure we can get to a couple of questions as well. So I encourage people who are more interested to have a look at the website. I've taken a look at this in advance, and I'm interested in this because the question that I would have for you, Mirza, would be obviously this does come with a price attached to it, but it seems to offer a more focused set of tools for robot arms compared to, say, ROS, which do Ignition, which is a free source software, but is versatile for all applications. So do you have any plans of releasing an API that is compatible with ROS so that people can use it with their projects and enable them to do more with their robot arms that way? Is that something in future plans?
Yeah, there are some plans to offer software to academic institutions, faculties, and others also, maybe for hobby projects, and I believe it will be free or something very with very small price tag, and software is primary focused for industrial robots and for companies which wants to connect to robot easily and to like some plug and play system to easy and quickly go and run robotics tasks, and but also I'm now is in some phase of looking for some investors and maybe people who will also join the project and from that it depends how this project will go further, and this is the first version for now, and I hope it will go in the right direction.
One thing I have been able to see as well is having a look, you have a very active forum presence, which is very nice. Often when you hear about this kind of smaller company software, they might say they've got great tools, but then if they're not supported by a community and supported by the developers, they're not much use. Whereas I had a quick look on your forum, and you can see that people who are using your software, and there do appear to be a lot of different unique users, are also able to get information, help, and advice from you very quickly. So that's something that I think, again, you're a smaller company with a more niche piece of software with a price tag attached to it, but in the wide ecosystem of robotics, that has its place. Do we have any more questions for Mirza? Sorry. No. Okay. I think we're good. How close are the features catching up to Stabuli or similar software? I will copy the word in for you in case I'm not pronouncing it right.
Stabuli, yeah, I heard for Stabuli robot.
You have to answer very quickly just because the time.
Yeah. For example, you just have to have a 3D model of Stabuli robot. You can import it very quickly in BabaCAD robotics and start a simulator. Also, if you have a Stabuli API, you can use it to connect simulator to the real robot.
Okay, thank you. Perfect timing. I'll ask you to stop sharing your screen now, please, and close your camera. And we will hand over to Evan from, as I check the website again, because I'm having to keep track of all the people here. Bottango, of course. Animating robots with Bottango, which is, again, another smaller software company here with a more focused application for how you can use robots. So, Evan, thank you for participating. Take it away.
Yeah, hi, thank you. I'm Evan McMahon. I'm the developer of Bottango. And first of all, just do want to say thank you again to the organizers for putting this together. Like a lot of folks probably organizing, I'm better at making things than I am about telling people the things I made. So it's really awesome to kind of have these opportunities to kind of show what I've been working on and to see what other people have been working on. So thank you. I'm looking forward a lot to seeing what everybody else is making or has, look at the presentations for this rest of this weekend. Yeah, so I'm Evan. I'm the developer of Bottango. Bottango is creative software for robotics. A little bit of background on myself, which I think will help make context of what this thing is and what it's used for. I'm a professional game developer. I've been in game development for over 13 years. And I kind of focus on two things, user experience and tooling. And I started building my own robots a couple years ago, maybe 4 or so years ago. And I approached it from, the way a game developer would, or, maybe somebody in the creative industry. I approached it from, wanting to not necessarily create something for utility, but create something for artistic expression or to capture emotional responses in the viewer of the robot. And I quickly found that the tools that were out there for hardware control, for robotics, that kind of thing, were very sort of utility focused and less focused on sort of a creative tool set. So I'm going to show you guys my first robot, which was probably the most advanced robot you guys are going to see this whole weekend. Here it is. It is a hacked together lawn flamingo. With plastic parts and servos, but you can see even in this very first robot, and this is years ago, the very first version of Bottango, like 00001. My sort of game developer instincts kicked in, which said, I want to control this thing with a 3D simulation and animate it the way I would a digital character. And if you look at how people animate digital characters, whether that's Cinema 4D, whether that's Maya, whether that's Blender, game engines like Unreal, Unity, across the board, 100% of the time, there is a standard workflow for how you create emotional movements. And by emotional, I mean movements that create an emotional response in the viewer's eye, as opposed to functional movements. And that's keyframes along a timeline with Bezier curves. I mean, that is universally just how it's done. Whether you're making a game, making a movie, making a TV show, anything that involves animating 3D characters for that end effect, that is the workflow. And nothing like that existed, as far as I could tell, for robotics and hardware control. The best that you could find would be something that sort of existed as an intermediary layer between a traditional 3D animation package and your hardware, but nothing where that treated that as a sort of first-class problem worth solving on its own. So that is the heart of what I'm doing with Bottango. Is it's sort of 3 elements combined together. It is a 3D modeling and simulation environment, so you can create the robot itself that you are, or a digital double of the robot that you're animating. One of the things that is important to me in Bottango, especially because of the kind of users that are out there, is completely robot agnostic. It's not like, there's these set robots that we support or something like that. It is, it's built so, that first and foremost, you are able to kind of control whatever unique one-off animatronic or hardware that you've created and bring that in. You're not fighting the system. If you have something totally unique, you're kind of living in the way it expects you to work. And so there's the simulation and the modeling package combined with a industry standard, creative workflow around keyframes, timeline, and Bezier curves, that kind of thing. And all of that united together with a open source real-time hardware control library that kind of is the yin and the yang of the whole system. So here you can see definitely more advanced than the flamingo I showed a minute ago. This is sort of a more up-to-date version of Bottango, and you can see here I'm animating the simulated character and the real-world character at the same time. You can see I'm manipulating this. I'll get into this in a little bit later. What that is, that's called a pose blend, but it's sort of a knob control to control multiple motors at the same time and animate it. You can see I'm scrubbing along the timeline. I can manipulate the Bezier curves here. I'm sort of saying, okay, this is the interpolation of this moment. Again, so I can control not just sort of the points of when and where the character reaches, certain points or certain trajectories, but control the timing and the exact interpolation between point to point, just like I would any digital 3D character. Here I am, manipulating and creating mouth movements and creating keyframes along the timeline, scrubbing, that kind of thing. So if you have any experience with traditional 3D animation packages, that's probably going to look really familiar. And that's the goal, is to be intuitive and build on skill sets that people already have that have experience in the animation world, and learn the best lessons that have already been established over decades of how to animate characters for emotional responses. Yeah, so kind of backing up a bit, in terms of the 3D modeling environment, there's basic modeling tools so that you can build the robot yourself. You can, like this in that image there, that robot's built out of entirely just the 3D modeling tools, or you can bring in your own 3D models. If you have something from a CAD or something like that you want to bring in and configure it there, you can. You can see here, this is a bit of just the configuration of the modeling environment, setting up servos. You're able to move the parts around, that kind of thing. And then there is, like I said, that fully featured 3D animation pipeline or workflow. You can see that's a much more complicated animation than I showed earlier. And here I am manipulating the shoulder joint, the elbow joint of this robot, and messing with, the interpolation of, okay, this keyframe between these two moments, how do I want, this to animate, and how do I want the speed and the kind of the follow through of these moments to play out. Yeah, and then all of that combines together with real-time hardware control, so that you are controlling, not just the simulation, but you are able to have that be a digital double and kind of see how your animation is playing out in real life, both in real time and playback later. One of the cool things about the hardware control library is, as opposed to sampling the animation over time, let's say, if my arm went from here to here and I took 30 samples a second or something like that, the way Bottango works instead is actually the hardware library receives the animation data itself, the keyframes, the Bezier curves, that kind of thing. And it does the interpolation both on the controlling computer and on the hardware in sync. And the result of that is, as opposed to the kind of communication bottleneck between the computer and the hardware controller being the frame rate or the bottleneck of smoothness, you'll have, because the animation engine exists in both places, you'll end up with thousands of frames per second, because microcontrollers can be pretty fast at just doing basic math. You'll end up with animation playback of thousands of frames per second smoothness, and on a motor especially, that makes a huge difference. And so that's one of the kind of the coolest parts about Bottango to me, is the playback is just buttery smooth, even if your computer is stuttering for any reason, because of that separation there. And that results in, I think, again, a better tool for helping capture that emotional response, right? Because, when you're looking at a character move and it's stuttering or something, or it doesn't have kind of that smoothness, just like if you were watching a low frame rate movie, it affects the the end result, which is that kind of emotional response to the movements. In terms of that that hardware support library, out of the box, just sort of sans code, just kind of, it just works. There's servo motor and stepper motor support. And then there is a workflow for adding, there's a API and, that kind of thing. Again, the hardware library is fully open source and just provided, but there's an API for adding your own effectors. I also do plan on continuing to add support for additional kinds of motors like Dynamixels, or, I hope to add like O-drive support for like BLDCs, that kind of thing. There's also a workflow for adding non-motors into your timeline. They kind of come in 3 different flavors: analog, digital, and trigger, which I call curved, on-off, and trigger events. So basically, let's say you wanted to control a light, maybe, if it's an RGB light, you want to control its brightness, or if it's like an on-off light, you can sort of turn it on and off. Or, if you want to have like, okay, when this trigger fires on my timeline, maybe this solenoid kind of opens up and confetti falls or something. So, excuse me, you have the ability to add non-motors and other kind of custom events to the timeline and animate just like you would any other, just like the motors in the simulation. And all of this, the hardware library itself is Arduino compatible. And I specifically, because it's important to me that this is something that can be as approachable and as accessible to as many people as possible, especially people that are tinkerers or people that are building their own machines. Kind of an Arduino Uno is what I call my min spec. So if it can't run on an Arduino Uno, which is pretty low resources, it's not a feature I support. So if you have hardware more or an MCU more capable than an Uno, you're going to be in good shape. But all of it is, the open source library is Arduino Uno compatible and obviously kind of continuing to add more hardware support and continuing to make that a priority. In terms of the ability to do that live control or the hardware playback, you really do have two options. You can connect your computer via serial to your microcontroller and use the library and have that live control playback. There's also actually even an API to control Bottango, the Bottango desktop application itself. So you could, for example, write your own Python script and talk to the Bottango application and tell it to play this animation or switch to this animation or move to this time point on this animation, play this far and then switch over, that kind of thing. So you actually can script Bottango, which can then talk to the microcontroller. Or you have the ability, there's a workflow to export the animation data and the animations itself into standalone C++ Arduino compatible code. So you can just sort of upload it and there's an API in that standalone workflow as well to allow you to control what's playing and when, that kind of thing. So you actually can kind of go entirely headless and create the animations on your computer real time, play them back, and then export it out and just let it run autonomously.
Okay, Evan. Just to let you know, I'd like to be able to move on to questions quick as well. So is this the last video?
Yeah, I'll give me like 45 seconds and I'll wrap this up.
Yep.
So we've got a really active community of awesome users, and mostly folks are on our Discord. I just want to show a couple, I love to show a couple things that some people have made using Bottango and control. This is one of my favorites, Tori's Flamingo, or excuse me, not Flamingo, Toucan. Yeah, here's another really cool one. Yeah, so, all right. I think we can skip to them. There's other cool things like inverse kinematics, stuff like that. There's all kinds of cool stuff. We've only got 2 minutes, so yeah, I'll rush through. It's free. It's entirely free. You can download it. It's very user-driven at this point, or kind of, user. Basically, what you guys want is what I'm building at this point. So, yeah, I'll just kind of open up to questions at this point.
Wonderful, thank you. And we can go a little bit longer because we're now going to the 15-minute break. But I do want to make sure that people can get that 15-minute break as well. So fantastic. And the response has been from the YouTube the same as mine when I read the application initially, which is we love the Flamingo. And I said yes based on the Flamingo before then looking at the rest of the software. Again, it's fantastic to see someone coming at robotics from a different perspective, in your case of animation and game development. And I can see there's the future of robotic software and simulation is going to be sort of coalescing, and you can already see that in the shared physics engines and lighting engines that a lot of these engines use. Do we have any other questions from the YouTube audience? Very exciting. I know that Boston Dynamics, Disney, Imagineering, etc., many other companies use simulators like this. Have you explored contact interactions in the animation pipeline? Contact interactions in the animation pipeline.
I'm going to assume that means, I'm not 100% sure what that means. I'm going to assume that means like, self-intersection where sort of error is.
No, that
you're sort of like,
I would take that to mean being able to see if you can actually handle touching or bumping into something. What happens if the robot hits a user? That's how I'm interpreting it. I might also be wrong, but that's my understanding.
Gotcha. Yeah, I mean, in either case, it was an earlier feature that is now turned off, but just from a lack of sort of user response and the support it took to continue to utilize it. But I might turn it back on at some point, especially around this. That basically did physics simulation on your robot. The end goal of that feature was more to sort of find places where, based on physics, there's likely a deviation between what your animation is. And, let's say you did a sudden quick movement like this, the physics engine would simulate, that's a really quick movement. You'll probably get a lot of bounce and kind of come back. The response to that was somewhat lukewarm. Okay. So sorry, go ahead.
No, I think we'll just go to the next one last question, please, and then we'll move on to the break. is there also an option to use smooth reference signals to generate feed-forward signals?
You know, again, like you said, coming at it from a different angle, those are terms I'm not personally familiar with. So I apologize.
No,
I'm a game
nothing
developer trying to figure out robots.
That's part of the value of the showcase. We've clearly found an opportunity for you to reach out to some of these guys and find a few more robotics features and hopefully a few more roboticists too that want to use your software. Thank you very much.
I love getting feedback, and I love taking user requests and building that into the pipeline and the roadmap. So yeah, I'll definitely look into that. Thank you.
Wonderful. Okay, everybody, we're going to take a short break now, and we're going to come back on the hour, which for me is 5 o'clock, wherever that is your time. Have fun. See you in a few. Okay. Right, welcome back, everybody. So our next presentation is going to be from Darko Lukic, who I believe is a lead developer at CyberBotics and is going to talk to us about a implementation of SLAM using ROS2, their Webots simulation engine, and the TurtleBot. So, Darko, if you're ready, you can put on your camera.
Thank you, Oliver, for an introduction. I have video prepared. Do you want to play it, or I can do it?
I think I prefer if you play it, if that's okay. If you share your screen and play it then.
Okay, perfect, yes. Give me a second. Okay.
We're not hearing any audio, so it might be that I do have to stream it, actually. Okay, can you send me the link quickly? Apologies, folks. Right, I have it.
Hello, my name is Darko, and I'm a robotics software engineer at CyberBotics. CyberBotics is a company that has been developing Webots open source robot simulator. And in this presentation, I'm going to briefly show Webots and ROS2 integration that we have been working on. First, to give you a quick overview, I will play this short video.
Webots is a modern robot simulator. It was engineered for ease of use, efficiency, high-quality graphics, and precise physics. After 20 years of commercial development, Webots became open source in 2018. Since then, the Webots community has been growing quickly.
Webots is natively compatible with Linux, Windows, and Mac. It is distributed through Snap, Brew, App, Turbo, and Docker. It comes with a large library of pre-made, high-quality sensors, actuators, and robots, including wheel robots, legged robots, drones, industrial robots, and automobiles. It is very easy to create your own components using the built-in graphical editor. Webots has been supporting ROS for years. However, we believe ROS2 is the next big thing in robotics. Thanks to the support of the ROSIM project, Webots brought the ROS2 integration to the next level. Your ROS2 application can now benefit from the power of Webots with almost no integration effort. Run SLAM with TurtleBot 3, use ROS2 actions, visualize a robot in Harvey's, transfer a controller to a real robot, and so much more.
Our vision is a perfect integration of ROS2 within Webots to provide the ROS community with the best robotics development environment.
Webots ROS2 integration is implemented in a Webots ROS2 package. There are three main segments in which the Webots ROS2 package makes the integration easier. First, the package automatically creates a ROS2 interface out to the robot model available in the simulation. It is enough to run Webots, select a driver from the Webots
Ollie, we've lost audio.
the ground mobile robot, you typically want to do some navigation. Webots ROS2 package is one of the examples we provide to demonstrate usage of SLAM navigation control.
Apologies, I moved back, folks.
We spend time on the integration, so we made sure everything works out of the box. And third, the package contains documented examples that you can use as a guideline or a boilerplate for your next project. In this simulation, we see a turtlebot burger doing SLAM. So if you work with a ground mobile robot, you typically want to do SLAM and navigation. Webots ROS2 package is one of the examples we provide to demonstrate usage of SLAM and navigation. It is actually fully compatible with the Turtlebot 3 package, so you can easily switch between the simulation and the physical robot. This package also features our ROS2 control plugin that allows you to access low-level control and use out-of-the-box controllers. In the case of the Turtlebot 3 example, we use a differential drive controller and joint state broadcaster. When simulating or building a robot, we often start with a UDF robot model. Therefore, we made sure importing UDF into Webots works well. The UDF to Webots tool allows you to import your UDF robot model into Webots. We plan to further integrate the tool into the Webots ROS2 package, so the UDF usage is even more transparent for users. When working with the robotic arms, we typically need some kind of inverse kinematics implementation and a motion planning framework. MoveIt is a great choice, so we made sure it works well with Webots and that we have a good example demonstrating its usage. Within the Webots ROS2 package, we implemented necessary controllers for MoveIt 2 integration. For example, a joint trajectory controller and joint state broadcaster. Webots has a long history of vehicle simulations. Besides the high-quality vehicle models, there are a lot of necessary tools for vehicle simulations, like real-time image simulation, sumo traffic simulation, and OpenStreetMap importer. All those things make Webots a good candidate for vehicle simulations. In the scope of ROS2 package, we provide an example with Tesla Model 3 that exposes the Ackermann topic, and the car also follows the lanes using camera. You can also simulate drones. We have an example in which we control a Mavic drone using ROS-Twist commands. Webots works in the web. You can check the robotbenchmark.net website, in which we host online robot competitions. Recently, we released a new web rendering engine built specifically for Webots in WebAssembly. For ROS2 users, that means that you can now record animated simulation, share it online, and users can play them. You zoom it, zoom out, move around, and so on. All that while maintaining the high visual fidelity of Webots. To recap, the Webots ROS2 package provides many examples that demonstrate Webots and ROS2 easy of use. We provide simulations for all kinds of robots, most notably for mobile ground robots, industrial arms, vehicles, and drones. You can use UDF robot models. The most widely used ROS2 tools like Navigation 2, MoveIt 2, and ROS2 Control are already integrated. And you can publish high-quality animated simulations to the web. Thank you.
Okay, thank you very much, and apologies about the technical difficulties there, folks. I was tricked. Thank you very much, Darko, for the video. Very informative, and I'm really interested about this software. So you're around to chat for a bit as well, right? You've got some time for Q&A then.
Yes. Thank you, Oliver. Yeah, I prefer to play. Sorry. I prefer to play video because I already recorded it and I wasn't sure I will be able to attend.
Okay, thank you very much. I've also taken a recent interest in Webots through its use in the RoboCup simulation. And what I'm wondering then is always about the question of reproduction. So we have a TurtleBot free at our university. If we wanted to go and replicate this work so far, what challenges do you see? Is it something where you've been able to put it in the hands of someone who's not worked with you and only seen the documentation and it can be reproduced like that?
I mean, it should. So the first challenge is probably like deploying the software on the robot. So you need some kind of software abstraction. So your controller can work with the simulated robot and the physical robot. That's the first thing. And the second one is a calibration of your model. So your model will not be perfect. It's approximation. So you have to put a hardware in the loop and to optimize model for your task.
Okay, thank you very much. Chris, do we have any questions coming in from YouTube? I've got, what was your general motivation for this project?
So it depends, like the simulation software in general, or like the TurtleBot simulation. So if you talk about the TurtleBot simulation, so TurtleBot is widely used in ROS 2, and we wanted to demonstrate that Webots works very well with ROS. And we perform the tasks that TurtleBot usually does, like SLAM and navigation. And that was the motivation. For the software, like for the Webots in general, I'm not quite sure. Like it was created like 20 or so years ago. And I believe it's created because the current CEO wanted to do some kind of simulations, and he didn't have access to the robot. So he created a 2D simulator, which allowed him to perform some evolutionary algorithms. And I think he went to a conference, and the software was very popular. He shared a lot of copies, so it was like 20 or so years ago.
Yeah, one thing I have seen with Webots is there is an advantage that it has over ROS in being more recent software is it doesn't come with legacy documentation. So the documentation for Webots is all very recent and therefore more likely to work, as often you can run into issues when the documentation was written 5 years ago. So I think there's often an advantage in that for using Webots. And I've seen you've got lots of models up there and you're working on, I believe there's URDF2 proto.
Yes.
In the works or currently in a stage of development?
Yeah, I think URDF to Webots, you can use it now. I believe it's quite stable. So it allows you to import URDF models. And regarding documentation, it's up to date. So every time we push a new feature or new change, in the same pull request, we update the documentation. And that's the reason why you always see the updated documentation. So documentation is not updated after we introduce many features, but in the same pull request as the feature. And that allows us to like push everything at the same time.
Okay, thank you. Chris, again, are there any more questions? Otherwise, I've got one more I'd like to ask.
Yes, we do actually have one. Well, looks like a comment. Webots includes a number of pre-calibrated models, such as the Epoch robot, which should behave very closely to the real robot when running the same controller program.
Yes, actually, I did my master thesis with Epoch, and I did some navigation tests and mapping tests. And the interesting part was that there were some errors in navigation and mapping, and those errors were pretty much the same in the simulation and the real world. So the simulation also captures the errors quite well.
Okay, I said I had one question. I realized I've got one more because we do have time. We may also, if our next participant is available, they may wish to start early if we're out of questions, because I know we've got a very interesting speaker next, as well as yourself. As someone who's, you know, mentally psyching themselves up to make the jump from ROS to ROS2, what would you say your experience has been like in that transition, and how would you rate the benefits of using ROS2 over ROS1 from someone who's been through that experience?
I wasn't really transitioning to ROS2. I wasn't like
you
some
started
kind of.
with ROS2.
I mean, I knew ROS1, but not like quite well. So there wasn't that much transition in my case. So one thing in particular that I noticed is that ROS2 is easier to cross-compile. So one of the things I was doing was cross-compilation of ROS2 for EPUC. So EPUC has a Raspberry Pi 0 on it. And there is no official support of ROS for ARM32. So I remember before I was trying to cross-compile ROS1, and it was successful, but it was very tough because some hard-coded path. In ROS2 case, it was actually easier. So that's one huge advantage. Also, I would say that there is no ROS core. There is no, it's not centralized, it's fully distributed, so you don't have to care much about the ROS core.
I mean, I remember when you're learning ROS, you're certainly always forgetting to learn ROS core the first couple of weeks.
Yes.
So that's certainly one nice feature, as well as you mentioned the cross-compiler. Okay, one final question before then. Benjamin, if you're happy to get started a bit earlier, would say, are there any plans for a 3D slam in the future at some point? Challenges be there?
No, in case of Webots, I mean, Webots is simulation software, so we're focusing on developing simulation. So we want rendering. We want to improve our rendering engine. We want to improve our physics engine, and we want to improve integration with third-party libraries like ROS, ArduPilot, or similar. So yes, okay. I think we want to focus on.
I think that's something where you're waiting for someone else to come along with the full put together ROS stack for something like that. Then you can set up with Webots.
Yes, exactly.
Yeah, that's not your focus. Okay, wonderful. Well, thank you for your time, Darko. Really
thank you very much for having me.
And yeah, fantastic work, and interesting to see where it goes. I'm interested to be using it next year for robot humanoids in RoboCup. So wonderful. Thank you very much.
Thank you.
And we will now move over a little bit earlier, ahead of schedule, to Benjamin Gibbs. Sorry, apologies.
No worries. Good morning or afternoon, depending on where you are.
For me, it's now getting into the evening.
Well, good evening, sir.
Thank you. Okay, so when you're ready, take it away.
Great. So I am joined by my colleague, Jake Huckabee, who is here on mute. I don't know if it's possible to pin him instead of me. He's actually going to run through the demo here. So I was going to share a couple of slides first really quickly. So Jake is going to pull those up right now. And then we're going to run through the actual Forge OS. We're going to demonstrate it live here in our production space. We're headquartered here in Columbus, Ohio. We're going to be showing you real-time control of a industrial robot that you see there. So that is a FANUC 710 IC50 industrial robot arm that is being controlled by Forge OS using this Kiba Keytop T150 industrial teach pendant that is made by Kiba. So real quick, background on us. I'm Ben Gibbs. I'm the co-founder and CEO here at Ready. Jake Huckabee is our VP of Strategic Initiatives, a PhD roboticist from Georgia Tech. And we're here today to talk to you about Forge OS 5 and the native apps that we've built on it with our APIs. So we're a venture capital backed company, headquartered in Columbus, Ohio, with offices in Baltimore, Austin, Texas, and most recently Oakland, California. Jake, could you move the slide to the next one, please? So this is the specific problem that we are focused on solving, is this issue of fragmentation. As I'm sure everyone on the call is aware, every robot arm OEM has their own teach pendant and their own programming language. You can see some examples here with Universal Robots, which has URScript, Yaskawa, which uses Inform, Sanic is Carol, so on and so forth. These are some of the more common ones, but as I'm sure everyone here knows, they all are different. And this is a specific problem that we are aimed at solving. And an important nuance as we start to walk through some of this stuff is our software platform is not a offline programming suite that uses post-processors. What we have done is gone in through the APIs for a variety of different robot arm OEMs and created a real-time control over these systems. Jake, could you please advance the next slide? So this is the overall structure of the software that we've built. So the Forge OS 5 is comprised of 4 main layers here. I'm going to walk through each of these very briefly. Next slide, please. The first one is the abstraction layers. So we have a device abstraction layer and then a robot abstraction layer that are specifically designed to abstract away all of the proprietary programming interfaces that are unique to the robot arms. But also what our software allows you to do is actually control devices beyond the robot arms. So you can use our software as essentially the controller for the entire robot cell. So grippers, sensors, pneumatics, all of that's also controllable through Forge OS 5. We support a number of standard industrial communication protocols, including EtherCAT, Ethernet IP, Profinet, and Modbus TCP. On top of the abstraction layers, we have what we call our core services, which is the manner that we manage all of the interplay between the connected hardware. Next slide, please, Jake. So this is basically what's managing all the different threads between the sensors and grippers and, of course, the robot arms. It is possible to control a plurality of robot arms with a single teach pendant. So we actually have a recording of our launch event live stream. At the end, you can see 3 robots from 3 different brands all being controlled through one instance of Forge OS. Next slide. On top of the core services, we have what we call our application layer. And so this is where you can handle view system, notifications, access libraries, and other resources, all with an eye towards building apps that enable different functionality for the robot. Next slide, please. And this is, of course, what we have used. So we've used our own APIs to build a set of core applications that we're actually going to walk through the main ones in just a second here with this live demo. So at this point, we're going to put away the slides and actually look at the real robot. So as I alluded to at the beginning of the presentation, this is a Kiba Keytop T150 industrial teach pendant running Forge OS 5, and this is our home screen. So this is much like you would expect with an iPhone or an Android device where you have a number of different apps that provide different functionality. We have some very basic ones like the settings app. We're not going to spend really any time on that one. That just lets you set the like system time and do some network configuration, that sort of thing. The 3 main apps are what we call device configuration, the device control panel, and task canvas. So device configuration, Jake, you go ahead and open that up, is essentially like add, remove hardware. This is where you can add a number of pre-configured devices. So for example, today we support both collaborative robots and industrial robots from ABB, Denso, Epson, Sanic, Stobley, Universal Robots, and Yaskawa Motorman. We'll actually be launching support for Kawasaki in about a month, followed after that by Yamaha, Kuka, and Nachi. So this allows you to go through some basic configuration. You can add Ethernet IP devices and other peripherals as well, all through the same interface. The next app is the device control app. So the device control app is exactly what it sounds like. This is where you can actually control robots and other connected peripherals in real time. So this is where when you are programming out a given task, you want to jog the robot around to different poses to use as waypoints, you can do it through this interface. So because this is an industrial robot, we use an industrial teach pendant that has a mode switch key, a dead man switch, and an emergency stop. And you can see that we have real-time control over this system. So Jake is actually jogging that robot in real time. We can jog it as he's doing in Cartesian space because we have built out all of the necessary inverse kinematic models and everything else you need to move it in Cartesian space. And then we can also move it in joint space. So the idea here is you can control the robot in the exact manner that you would expect to be able to control industrial robots through their traditional OEM teach pendant, but you have a uniform interface. So whether it's a FANUC or a Yaskawa or a UR, you can control it directly through this interface. You can jump the robot, you can jog the robot, you can set tool center points and payloads, basically all of the functionality that you would expect, again, from an OEM teach pendant. And then finally, we have the crown jewel of our apps, the one that we call Task Canvas. So Task Canvas is a low-code programming interface. If you're familiar with Scratch or Blockly or those type of interfaces, this should look very similar. You basically chain together what we call building blocks into a flowchart. And so this is designed so that people that aren't programmers by nature or have no background in robotics can very easily program out a wide variety of different tasks and tasks of increasing complexity, starting off with a very simple and easy to use interface. So an important thing to note with the platform that we've built is that it uses a plugin based architecture. So if we don't support a hardware device today, doing so just requires the development of a software device driver that plugs into our abstraction layers and core services. And when you add a new device, you get that functionality in a modular fashion. So when you add a building block here in Task Canvas, the options that are available to you are based on what devices you have connected. So if Jake clicks one of those blocks and clicks the add button that crops up here, so we have the ability to add a number of different blocks. We have some devices connected already. You can see there's a menu for the 710 IC50. There's one for grippers. There's one for what we call the Forge controller, which is basically just a plug and play industrial panel that has PLC and pneumatics and other things of that nature in there. So again, this is something designed for modularity and also ease of use. And the important thing to note is that this app, Task Canvas, along with all of the other apps that we've showed you today, can all be built or have been built using our APIs. So one of the things that we're actually pushing towards here, because we've done this in a very API-driven fashion, is enabling developers and enabling other people to do interesting things with this platform. So we're actually in a closed beta right now for the Forge SDK. We're going to be accepting applicants for the next wave of that closed beta in about 3 weeks, and then continue to onboard additional developers until we finally publicly release the Forge SDK in the late October, early November timeframe. The idea of the SDK is that you can build whatever software functionality that you want on top of our APIs. We have no pride of place when it comes to things like Task Canvas. We think it's useful for certain types of applications, but not necessarily every task that a robot wants to do. Like everything else in the system, you can actually use the Task Canvas APIs to build your own building blocks if you do like that interface. And if you don't, you can create your own interfaces with it. Also, you will be able to create your own device drivers. So if you've built your own unique hardware and want to leverage Forge OS as the software layer, that's something that is also possible using the SDK that we'll be launching later this year. The idea is, we want to empower developers to be able to do all sorts of things and hopefully continue to push the envelope of robotics forward, which is why we're going to be offering those developer licenses for free to whomever is interested. So that's pretty much the long and the short of it. There's certainly other functionality in Task Canvas we could show you. I know that we have a very limited amount of time though, so I'm certainly happy to open things up for questions.
Well, fortunately here, our previous participant had been allocated along the slot into me, so you still have another 15 minutes here. So if there are more features you'd like to show, feel free to. That said, I've also got a few questions, so whatever works for you.
Why don't we start taking questions, and then we can use that as a way to maybe organically show more capabilities in the system.
Okay, well, I like to say this looks fantastic. As someone who did a brief part of a module at university working with some old Mitsubishi robot arms and a software that looks like a minor improvement upon Visual Basic, which was trash compared to this. So I can completely see the need for this, and I can see the need for uniformity in it. The fact that the SDK you're saying you're making it free to develop is great, because I can also see, of course, there's a gap in education between the tools that you can teach for industry, because industry are often using proprietary software. So if this is something that can be enabled for teaching, the new robotics courses that are cropping up around the world at universities like mine, for students and undergraduates to get their hands on with these tools, they can then go into industry prepared and go to second and third year placements and graduate placements again with that tool set in hand. Don't know what your thoughts are on that.
No, that is something that we are very keenly interested in supporting as well. The way that we see it with educational institutions, and we started to do this in a limited fashion here in the United States with a couple of technical centers, where we are providing licenses for free. And that's something that we intend to continue to do. There's obviously a commercial cost if you're going to deploy this in a production environment with one of our runtime licenses. But if you're not using the runtime license, the idea is this is something that we will absolutely be providing free of cost. And the educational one is one that I think is very important, because you rightly identified the issue where, because these systems are proprietary from the OEMs, a lot of times universities are using free software that doesn't necessarily translate into production environments, or they've tried to pick one, right? They may teach FANUC or Yaskawa or Mitsubishi, and that doesn't really prepare people for the multiplicity of interfaces that are out there. And that's ultimately why we see that educational side as being very important, because we can start to teach people on essentially what's a common interface that once they graduate and go out into the world, all they need is an industrial PC running this software, and they can control any robot out there to their, as much as they would like there. We actually do have a case study on our website from one of our educational partners. It's an institution called eCanny that reskills former coal miners in Eastern Kentucky. And so these guys come in literally having never seen a robot before. Over a 2-week period, they go from knowing nothing to being able to program robots from different brands using this same interface. And these are smart guys. They're very mechanically inclined. And like you, right? I have the same reaction. Someone hands me an old school Teach pendant, and it looks like an oversized graphing calculator from the 1980s with a tiny LCD screen. Overly complicated, unnecessarily so. And it's intimidating. I get intimidated by those pendants, right? Providing a modern interface that is easy to pick up and sort of get started with provides people with the confidence that they can then do the more complicated things, which is what we see happen.
Wonderful. And of course, it is a tried and tested strategy by CAD software companies in the past, that if you can train, the next generation of your workforce on your software, that's going to then encourage sales from the companies, because they're not going to want to go investing in something that they then have to teach people to use. So there's obviously a benefit there, but that's a benefit of success. If that's something where you're doing things right, the money comes naturally normally in robotics.
We certainly hope so.
Are done right. And I guess the SDK will have then ROS support connections. As a lot of these ROMs can already be set up with ROS, and this is just another a tool to complement that in the overall ecosystem of robotics?
Yeah, I think what Ross has done has been tremendously valuable for robotics, and ultimately the vision that was laid out by the original founders of Ross is a noble one, right? And a necessary one for the industry. We very much so want to support the Ross community and do have designs for some type of Ross bridge so that you can plug in a lot of this existing stuff to our architecture. Like many robotics companies, we got started using Ross. We've now since built our own proprietary stack, as you can see here. But Ross itself, I think, is tremendously valuable, and it's certainly a community that we intend to support to the fullest extent possible.
Wonderful. I have one question here. Making a custom robot at home, spending a lot of money on it. Any chance I could interface with the API easily despite the custom hardware?
So that is certainly something that we would be interested in finding out collectively with you. The SDK documentation and code examples, that's still actively coming together right now. But one of the use cases that we very much so had in mind is people that are building their own robots at home and may have a novel design, an interesting approach to it. And we want to be able to enable you to write that driver to plug into the rest of our stack so that you can focus on really optimizing that design, not having to do the tremendous amount of work of building not only the hardware stack, but the control software stack as well. So certainly something that we would be interested in exploring further. I don't know how we disseminate my contact info if they want to reach out directly.
I'm in touch.
Great, fantastic.
Wonderful. And I actually think you sparked an idea there. I can think of someone else I know who may have an interest in it. I'll see if I'll send them an email about that. Do you have any more you'd like to demonstrate with the remaining? You've got 5 or so minutes.
Yeah, so a couple of other points real quick that we can show off. We have the capability to do subtasks as well. So one of the things that you can do is build out very complicated flow logic that can also execute simultaneously. So Jake has some examples up there, right? So these are basically subtasks that can either run simultaneously or sequentially, depending on what kind of logic that you want to set up. But again, this demonstrates the overall extensibility of the system. I would say also, please reach out to me if you are interested in participating in the closed beta or have thoughts on how you might be able to leverage Forge OS. We're interested in supporting the builders, the dreamers, the developers out there that, in my opinion, are going to be how we drive robotics forward. The International Federation of Robotics, their last report, 337,000 robot arms sold globally in 2019. I think that number, while commendable, is off by a couple of orders of magnitude. Where we really need to get as a global society is one that embraces robotics and automation and get to a reality where it's not 337,000 robots sold, it's 337 million robots sold. There should be robots everywhere, helping everybody, and ultimately lifting up society much in the same way that automation in agriculture has done so. And I firmly believe that it takes a village to get there, which is why we are so keen to support developers however we can. And I think solid evidence of that is not only will we be providing developer licenses, but we've just hired a new VP of developers who's in charge of really championing that voice for developers. And he comes to us from ARM, where he previously built developer communities at ARM and also at Arduino as well. So he is himself a developer and will be the voice for you all as developers as well. So please reach out to me. We're keenly interested to talk to you all, very much so interested in supporting whatever projects you are looking to build, whether it's in the closed beta now or in the future when the SDK releases. So just wanted to thank everyone for your time. Thank you for the opportunity to present here. I, for one, am tremendously excited about what the future holds, and I'm very excited to have the opportunity to just showcase some of our work here today.
Wonderful. Do you have time? I've got one more question if you have time for it.
Absolutely.
So you mentioned about, obviously getting an order of magnitude up, which I think you're preaching to the choir in this community, of course. I know that one of the key issues for getting robots out into the real world is their ability to work safely around people. These are collaborative robot arms, and examples like the universal robot or ones that have stiffness compliance. Is that something that your software supports, being able to sense for an impact potentially or a collision, things like that?
Yes, so you can add force sensors to the system as a peripheral if you want to use a force torque sensor for some very fine movements, that sort of thing. The other thing is we actually just do support the cobots as well, right? So Universal Robots is a line of cobots we support. We also support cobots from Yaskawa, Fanuc, ABB. We ourselves don't make safety hardware or software. So what we do is our software basically takes cues from the onboard force sensors in those arms, right? So like a UR cobot, for example, right, has a force sensor in every joint so that when it feels too much feedback, it goes into a protective stop. And that behavior works identical whether you're using Forge OS or the native UR software.
Okay, wonderful. All right, thank you very much. We have a few minutes now until our next presentation from Tuur of Studio Technix, improving robots with multi-domain simulation. So I think we'll take a quick pause. Benjamin and Jake, if you could kill your feeds when you're ready to. And thank you very much again. Really exciting presentation. And I will be in touch at some point in the future with my own interests. Thank you very much again.
Thank you so much, and talk soon.
Okay, everybody, we will meet back in 5 minutes. Okay, thank you everybody who's joined so far. It's been a good session so far and we've done well, and it's been great to see the number of people who have been watching via YouTube. Our last participant for this session before we take a break and then move on to mobile robots, which I'm very excited for as well, is Studio Technix improving robotics with multi-domain simulation. It's been great to see such a interesting variety of approaches to software from our community, from people at different levels, from startup companies to, all startup companies in this case, but startup companies with very different sizes in different places. So it's interesting to see their approaches. I will now hand over, if you're ready, to Tuur. When you're ready, you can put on your camera. Wonderful. I hope I'm pronouncing that right, by the way. Please do correct me if I've got it wrong.
It's okay. My name is Tuur, so you did pretty well, yeah.
Okay, thank you. When you're ready.
All right, thanks. So, hi, I'm Tuur. I'm an engineer with a background in simulation. So in the past, I was a research engineer at Siemens, where I did different projects, where I did mainly simulations of aircraft and helicopters with projects with Airbus and Boeing, Embraer. And since 1 year,
Can I just check if you have a presentation to share at all?
Sorry, yeah.
No, that's fine. Just check.
I don't have a presentation. I will show my tool in action.
That's absolutely fine. I just wanted to make sure that you weren't going on a presentation without it. I'll let you carry on.
I'll start sharing my screen already. Here we go.
Wonderful. Okay, thank you very much.
Yeah, so what was I saying? So I'm now starting my own company where I'm building a new kind of simulation tool for robotics and embedded systems applications. And so the main idea is that you can couple any kind of program, C program, to a simulation model. And in this way, develop the software for a robotics system or an embedded system much faster by doing everything first virtually, and you can experiment quickly and test different kinds of scenarios, and only later go to the real hardware. And at that time, most of the software bugs will already be eliminated because you experimented digitally. So here you see this tool in action. It's called Studio Technix. I'll make this full screen. So here we see a simulation. Maybe I'll restart it. This is a simulation of an application. It's for a company that makes cleaning robots for solar panels. So the idea is that there is a drone, and this drone carries two little robots, and these robots can clean solar panels. And so the drone drops off each robot, and once the robot is dropped off, it will start cleaning the solar panel. And once it's ready, the drone will pick it up and will put it on another solar panel. And so this is here simulated in real time. So this is actually running 3 embedded applications. So the drone software and the 2 robots software is running in real time. And yeah, the software applications get input from virtual sensors, and they also have virtual actuators. So you can see, for example, if you look at these little robots to detect the edge of the solar panel, they use a distance sensor, and you will see when the robot at the edge, you see the red stripe. That's basically a visualization of this distance sensor. And so the distance is measured in the simulation environment and sent back to the simulation model and to the application. Okay, so this is one example. Let me now go a bit deeper into how the application or this tool works. So I'll do that by starting a new project. And this time it's, let's say you're a developer of scooters. So this is not really a robotics application, but still it's an embedded system where you have a scooter for some kind of sharing service in a city. And so the scooter needs some kind of software that runs on top of it to control different aspects, like to do the communication, to control the speed and everything. And so the idea of the tool is that you create a model of the system by dragging and dropping components from a library. So here on the left side, I have different kinds of libraries. And for example, my scooter probably has a button to lock or unlock the scooter. It probably also has some kind of display, has a couple of lights, also has some kind of throttle. So I can represent that by a knob, something that you can turn. And the scooter can also steer. And so the steering, it's also just turning something. So I will also represent this as a knob. So here it's represented as a 2D, icon. It does not really have to look like the real thing, but just has to represent what the real thing is doing. And then we also have this special application component. And this application component will contain the code of the system. So the code that's actually running on the scooter. And so typically an embedded system has a couple of, and a robotic system has a couple of inputs, like some digital inputs and outputs. I'll add another digital output here. Probably also has some kind of analog input to read the value of the throttle. And maybe I will use a serial interface to communicate with the display. And then I can complete the model by making connections between the different components. And so my application, for example, will send data to, or like control the lights, and will send some data to the display. And this way you create a model of the system. I will now show the completed model for the scooter. So this is a bit more elaborate. So what have I added as well here? So there is on the left, the bottom side, all these different components. These are components from the signal library, and they are basically mathematical blocks. And in this case, they compute the position of the scooter based on its speed and its steering angle. It computes its location, and then it's going on my other screen. And then it's displayed on a map. And we'll put the map here. On the bottom right here, you can see there are also a couple of mathematical blocks, and they compute based on the speed of the scooter, the power it uses, and also the battery charge. And so this can also be plotted on some kind of graph. And here I also plot the motor speed. And so once I start the simulation, you can see the simulation comes to life, and actually inside this block I already programmed a couple of things. And so this is now running in real time. And so I can, for example, lock or unlock the bike, and you can see the lights changing. Or I can start driving. I put the throttle, increase the throttle, and you can see on the graph that the speed is increasing. The battery charge is going down. And you can also see on the map that I'm moving. I can steer, for example. In this case, it doesn't take into account like the real roads. It's just a representation, because we can then in this case test some scenarios. Like I will stop here. This is in Washington, DC. And in Washington, DC, here there is a zone at the National Mall where you can drive your scooter, but you cannot park. And so if I try to lock my bike here, you can say it doesn't work. And some kind of error is displayed on the screen. This is one scenario that I test. I can try another scenario. Here there is a zone with a slow speed. And if I drive in that direction, you will see that my speed will automatically drop once I enter in that zone. So I'm not doing anything, and you will see, like, okay, the scooter slows down. So these are the kinds of scenarios you can test. You can test all different kinds of scenarios. And this example is just to show how the tool exactly works. Maybe now I have to show also how it works, the connection with the code. And so in this application block, the blue block here, this is actually a connection with some kind of C application. And I have the application here open in Visual Studio. But it doesn't really matter which kind of editor you use. You can use any code editor. But in this IDE, I program my application like I would do for the real device. And instead of using like a real hardware abstraction maker, I'm using this kind of functions here, ADC read, GPIO, pen set. These are functions that are really similar to what you would use if you program this kind of application for a real device. But what these functions do is they communicate with the simulator. And so you write the code like you would do for the real device, and you just get the simulation for free. And then you test everything virtually. And once you're ready and happy, then you can port the code to the real device. But that's very simple. It's very easy. You can almost copy the code. Like you only have to do small changes because these functions are very similar to the functions that a real hardware abstraction layer would provide. Like if you use an STM32 or an ESP32, you will have functions that are really similar to these ones. Now I will go back to the first example.
Just to say, if you're able to wrap up within a minute or two, just so we can move on to some questions, if that's okay.
Sure. Maybe the last thing I want to show is the 3D environments. So here you see again the solar robots. Voila. And so this is a simulation of 3 different systems in real time. And this is connected to this 3D block. And this 3D block is basically Unity 3D, the game engine running in the background. So I have here the same project open in Unity 3D. I can create any kind of environment with this 3D engine. It's very, very easy to use. And I make a connection with the simulation tool by dragging and dropping these kind of scripts that are provided with the tool. For example, if I want to add a distance sensor, like I said, you just drop the distance sensor on the robot, and you can then fill in the parameters of the distance sensor, and it will automatically make the connection with the simulation tool, and then you can get like an output port here, and then you can connect that with any kind of other component in the simulation tool. And so that's how it works for 3D environments. But the idea of the tool is that you can do this for different kinds of domains. If you want to simulate thermal systems, you can drag and drop thermal blocks that model some kind of thermal system. If you want to simulate some kind of fuel system, you connect fuel system blocks. If you want to do a simulation of some kind of pneumatic system, you can connect some pneumatic pump and so on. So that's a bit the idea of the tool. I hope it's clear. And yeah, that's it.
Okay, thank you very much, Tuur. Really great presentation. I really like the software. It's got a lot of unique features, like seeing you drag and drop a sensor and just have it attached onto the robot and be effectively ready to use there. It's something unique that I've not seen in other packages. How do you see your software fitting into the wider robotics ecosystem?
Yeah, so it has some features that are similar to other tools that are there. What I would like to focus on is that you can use these kind of libraries that are multi-domain. So not only the 3D environments with the typical sensors like accelerometer and gyroscope and some kind of distance sensor, but you can also add different kinds of components, like I said, like a thermal system, if your robot is controlling something that has thermal characteristics, or if you have a big system, a big machine that has a lot of pneumatics or hydraulics, that you can also simulate these kind of aspects. But also like communication, that you can simulate communication with an external server. If you have like an Internet of Things kind of system where you have to connect with some kind of external server, that you can also simulate this communication data and see how the robot reacts on that. So that's a bit the idea of the multi-domain simulation.
Okay, I've got a question from YouTube that is asking, is a battery submodel and scooter an example based on Coulomb counting? But I think a question more applicable to wider robotics is, does the software have co-simulation support? I'm not sure what they mean by co-simulation. Maybe you do.
Yeah, so I thought it was something about the battery model. No, the battery model it's a very basic model. It's just a formula with there's an integrator block inside. So it's like differential equation modeled inside the tool. Co-simulation is something that's definitely possible. It's not in the tool yet, but so co-simulation is when you can couple two simulation tools. Like there is like a standard FMI. So FMI is a standard to couple two simulation tools together. So if you want to simulate something that's very easy to do in one kind of simulation tool, then with the co-simulation interface, you can couple the two together. So it's not there in the tool, but there's no like technical limitation that it would not be actually it would not be too difficult to implement.
Okay, wonderful. Chris, do we have any more questions?
Yeah, we had one person ask about custom models in the program, adding custom components and things.
Yeah, well, that's actually something I'm currently working on at the moment. It's not at the tool, the version that's on the website at the moment, but yeah, it's a basic thing that should be there, and I'm working on it.
Okay, wonderful. Thank you very much. Again, this is really interesting, and I've really enjoyed this session to see such a diverse set of software and different approaches from different people, with some overlap and some unique variation on the themes. So we're now going to take a 1 hour break, and we're going to come back on the next hour for our next session, Mobile Robots, which will be a separate YouTube stream. And I highly recommend that in this hour, you take the time to share the links with any friends, colleagues, or anyone else that you think might be interested in having a look. It's a great presentation keynote. We have Mark Emerton of UK Research and Innovation talking about their £117 million challenge for robots for a safer world. Things like offshore wind turbine inspection and nuclear decommissioning, things like that. So I hope to see you all in an hour. Thank you very much.
Thank you very much. Thank you for the opportunity.
Yes, thank you. Thank you.